good afternoon, everyone. Welcome to this edition, this September edition of the famous mini-schools. Yeah, my name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. Yeah? And it is a great pleasure to introduce you to Professor Martin Bucher. Martin is based in Paris, as you can see on his slide. Yeah, but he's also affiliated with UKZN, and he's also affiliated with NITheCS because he's a NITheCS associate, and he's also one of the PIs of one of the NITheCS research programs at the moment. Yeah, and yeah, Martin has a very distinguished CV, yeah, that I won't read to you because it's on the announcement of the webinar, and we are really happy that that he agreed to share with us some of his knowledge in cosmic microwave background. And you know, I can advertise that he's writing a book on the topic, so you will be the lucky listeners of some of the chapters, yeah, of the book. Before I ask Martin to start the presentation, his slides are already shared. I want to launch a quick poll that should appear now on your screen. So that Martin asked to have some information around the background, about the background of the audience, whether they are undergraduate students, postgraduate students, whether they had cosmology lectures before, or so that he can tune the level of the course appropriately. Okay, I see the poll is slowly showing some trends. Yeah, we can leave it open for a few minutes. I think around 60% of you have participated in the poll. So if a few more would like to take part, we can give Martin a feeling of the lab. Okay, Martin, it looks like not many more people are taking part in the poll. So maybe we can stop it now and I can share the results. Here they come. Yeah, so you see, most people have had some cosmology, astrophysics experience before. Yeah, and the rest is a little bit of a mix between undergraduate, honors, masters, and several PhD students. So that's I'm not sure if you have some information now that allows you to fine-tune your next presentation, but we can do it again next week and see if it changes. Yeah, okay. So thank you very much for participating in our little poll. Martin, now it's over to you. And sorry, you always should encourage people to use the Q&A facility to ask questions, and Ilya, that most of you know by now, we'll also keep an eye on it so that Martin doesn't have to stress with checking questions while he talks. Yeah, Martin, please, over to you.
Okay. Well, first of all, thank you very much for having me. I sort of realized from the poll, I didn't know what level to pitch this, but it seems that most of you have had astrophysics or cosmology before. So perhaps I will make the next lecture a little more technical. This lecture is going to be a bit intuitive, and let me first explain the choice of topics and sort of tell you where this all fits in. So well, we're learning lots of things about the universe now. Astrophysics and cosmology has been a sort of area of very active progress. And it's sort of a bit ironic that we know more about the initial conditions of the universe than we know about, what happened after in the sort of dark ages where the first stars and quasars formed. So this is sort of the new frontier that will be explored by the SKA. And that's largely because of the cosmic microwave background, which is still a very active field, but maybe 2/3 of the discoveries have already been made. So the sort of point of these lectures is I wanted to explain to you how we know the initial conditions of the universe. So this is, I mean, that's sort of a rather immodest description, knowing the initial conditions, and maybe it's not completely fair because in the very beginning, we don't know what happened. There's inflation and there's a lot of speculation, but the cosmic microwave background is a moment where the universe was 1,000th of its present size. And more importantly, the perturbations weren't large, so you can use linear theory. So the theory is very simple. It's a very clean part of astrophysics. And these initial conditions, so why do we call them initial conditions? Well, they go into these huge computer codes that evolve the universe forward in time and take into account the nonlinearity of gravity, star formation, feedback, all kinds of radiative transfer, and it's very difficult. And this is sort of simple physics. So we sort of know what to start in those codes, but we don't know a lot of the physics that's very complicated to predict with any degree of certainty the things the SKA is going to look at. So I want to emphasize this sort of very early universe physics. Let's see. Oh, okay. I have, so I think these slides will be made publicly available. And I wrote this review a number of years ago. So if you want to find more details, here's an archive number. And, there are a lot of more formulas and calculations. So this is a good place to look. So let me start with describing some of the observational foundations. So this is a photograph of radio galaxies, and that was taken before the discovery of the microwave anisotropy. And what you're supposed to see here, with the exception of a few blemishes that can be explained in different ways, is that the universe, when you look at very large distances, is very close to isotropic and homogeneous. So this is supposed to look, if we don't look too much in detail at it's pretty close to just a random Poissonian distribution of points that have sort of been projected in equal area. So if we look at the history of observational astronomy in the last century. It's sort of been a quest to reach the largest accessible distances. And, you know, now, especially with James Webb Telescope coming online, we can look almost back to the Big Bang with galaxies and things like that. But it's been a little like going from the beginning of an onion and outward. And here radio galaxies were used because they're very bright, so you can see very far out. So the basic sort of observational fact.
Sorry, Martin.
Yes?
There is a question in the chat. What are these white spots on the map?
Oh, well, they're sort of blemishes where you can't see. Can you see the hand?
Yes.
Yeah, these are imperfections. And if you look in people's book, there are explanations of them, and also near the edge in this. So you should ignore that. But they have an explanation that they're not cosmological.
Okay, thank you.
So the basic picture, and we will explain why, is that you know, close by you have a lot of empty space, and the universe is very clumpy, but then you go to larger and larger scales and average out, and everything is quite smooth. Okay, so the other sort of pillar of observational cosmology is the expansion of the universe. And this was the object of a lot of controversy, because just on aesthetic considerations, you would like to generalize the Copernican principle, the time. But then you see this linear recession velocity law. And one interpretation of this is that the universe is actually expanding. And then the corollary would be that if you go backward in time, the universe got denser and denser and hotter. So this is the sort of hot Big Bang model. And this attracted a lot of controversy because people like Fred Hoyle would say, oh, well, the expansion rate is very slow, and maybe matter is spontaneously generated, and the universe is actually eternal. And there are actually people today who continue to argue about this. So Narlikar and Ayuka in India still disputes this and comes up with very clever models that try to sidestep this conclusion, but the evidence has gotten stronger and stronger. So this value should be updated, and there's a lot about the exact value. Was there a crisis? And that's something we can talk about later. Parsec is 3 light years. So astronomers like to use weird units that are somewhat unfortunate. So here is, this is to consider, if you consider the universe as sort of being spherical, it's like a balloon being blown up, and as a balloon blows up, well, if it were spherical, there would be no special point, but things move away from each other because of the stuff in between getting thinned out. So you get a rather nice picture in lower dimension of what an expanding universe is. Okay, here is Hubble's data from 1929, and you see this is not precision cosmology. Now we're approaching the percent level on various parameters, including the Hubble constant, although there's some dispute about that. But you can see the trend through here. And you also see that the normalization is completely off because of the cosmic distance ladder. There were two types of variable stars that were two populations that are different, and that wasn't recognized. I mean, I like to think about cosmology a little about, well, focusing on the observations and what do you see actually, and keep the theory a bit separate because you really want to know what evidence you have for things. And, you know, one of the big quests has been to survey the universe and measure distances, and that's sort of hard. So one of the techniques, recession velocities are easy to measure because you have spectral lines, and if you can get enough photons, you can resolve these lines very accurately. So it's easy with a big enough telescope to get redshifts. But then to find out the actual distance and compare them, you have to know how bright something should be. So the picture is, well, we have these candles and they're all the same. Hopefully, when you go out to large redshift, conditions change. And, you know, a lot of observational astronomy is finding and characterizing standard candles. And we can also go beyond the Hubble law. So the Hubble law is like a power series expansion just in our immediate vicinity. And then as we go out to redshifts of 1 and beyond, then you expect quadratic and higher corrections to come in. And you have these different curves. And these are supernovae, which are supposed to be standard candles. And this is from about 96 when it was discovered, contrary to expectation, that the universe is accelerating. So this is taking the distance versus redshift and fitting it to different cosmological models. So this is one example where the theorists really went wrong. They were insisting there's no cosmological constant because it's so ugly, and they love this cold dark matter theory, and supersymmetry seemed to explain the cold dark matter, which has not yet been seen but is needed for other reasons. And here you see that, well, you need something else. So this sort of highlights the importance of observation. I mean, a lot has been done just based on theory and beauty, the solution to Einstein's equations for these homogeneous and isotropic universe versus dates from the 1920s with Friedman's work, but there was no reason to have any confidence that these solutions would really describe our universe. The evidence for the homogeneity and isotropy on large scales was not there. So that was something that was theoretically explored, and then it took a very long time to develop the instruments to be able to test this theory. Okay, this is a more recent compilation of this curve. So this is mapping the expansion of the universe, and then other people are going to do this in, with baryon acoustic oscillations, and also with the SKA and Hyrax. So those are sort of exciting things in South Africa in this area to collect observations that have different systematic errors. Okay, so this is, if we sort of summarize the Big Bang Theory, is, you know, what are the conclusions? Well, as one goes backward in time, the universe becomes smaller and smaller in size. And if one extrapolates all the way back to zero, then you get an infinite temperature and an infinite density. So there are all sorts of questions that arise. Can we just take our what we know about matter and just extrapolate back farther and farther? And does it make any sense theoretically? So that's something we're going to talk about later. Okay, smaller size means a hotter universe. So if entropy is conserved, and it isn't necessarily, entropy can be created in phase transitions and other processes, but assuming that entropy is roughly conserved, you are led to the extrapolation that the temperature will diverge to infinity. So does that make sense? Do we think that we understand physics there? Well, this is also an opportunity that is experiments such as the LHC are sort of at their limit. You know, we cannot go many, many orders of magnitude higher in temperature. The world isn't big enough for, you know, such a collider with present technology, and the world economy isn't big enough to pay for it. So a lot of the emphasis on cosmology is to try to use observations of the universe to, you know, go up to much higher temperatures, because what happens at these early times relies on physics beyond the standard model. Okay, so this is a diagram, not very to scale, giving you different sort of mileposts. So, and we'll talk about how far back we can test this extrapolation. So today we're, well, this diagram is a bit old because the age now is shorter because of the cosmological constant. So the universe is believed to be a lot younger, but the temperature, which is now the CMB temperature, is the CMB is cold, but it carries most of the entropy. And then as we go approximately 1,000 times smaller, so linear dimension, so that would be 1 billion times smaller in volume, then we get 3,000 Kelvin. So that is the temperature at which hydrogen will ionize. So before that, you have this plasma where the electrons are not grouped around the protons, but free, and the universe is very opaque. So electrons scatter through Thomson scattering, and this is the, this isn't very hot. If you take your arc welder, you can make a temperature like this. So we can be pretty confident that unless something really weird happens, that we know what the relative physics is, then we can go back farther. Well, we think that we know what, we sort of understand nuclear physics. We might not understand how nuclear physics comes from the QCD Lagrangian, but there are lots of cross sections and effective models. And this can be tested. Then the speculation sort of piles up. So we go to the quark-hadron transition, and that would be arguably probed by heavy ion collisions, maybe not so much, because that's not necessarily equilibrium physics. Then we go to the LHC, the electroweak phase transition, and then this would be 10 to the minus 11 seconds after the supposed Big Bang. And then it's sort of all speculation. So, grand unified theories are nice, but they have a lot of problems and haven't been proven. And we sort of know that something is going to happen at the Planck era. So this plot sort of makes clear what is the connection between new physics at very high energies and observations of the early universe. And one of the things I want to talk about is how far back can we go and have any confidence in these predictions. So there are a number of predictions. First of all, in this theory, we cannot put in, the ratios of nuclear species is an initial condition, because everything was sort of, all the nuclei were initially very completely dissociated. So this is one of the things that should be explained by the theory, that when you start with an initial condition very hot, where you have the only free parameter is the number of baryons per photon. So that's baryon number is believed to be conserved at maybe not near the Planck scale, and there's some electroweak violation, but it would be very small. So from that one parameter, we should be able to explain all of the nuclear abundances. So that's bit of a complicated story because there's also nucleosynthesis in stars. So the primordial nucleosynthesis would be, well, what are the nuclear abundances? And if you have the nuclear physics, you know the rate of the expansion of the universe, you should be able to predict all of that. So here is some sort of basic nuclear physics. So that here we have the nuclear binding energy is a function of the mass number. And this diagram is a little deceptive because it only includes the most stable nuclides, but you see that around iron 56 is the most stable, and you get hydrogen here, and the alpha particle or helium-4 nucleus gives you a lot of stability. So for those of you who have studied nuclear physics, you have two complete shells, both in the proton and the neutron. Then the binding gets less, and you get more and more stability. But what you learn from this diagram is that the physics that determines the present nuclear abundance is non-equilibrium, because otherwise you would be in here. This is what would be energetically favored. So what primordial nucleosynthesis tries to do, and here I have it sort of written out in detail, is you follow the rate equations, and so you have species colliding, and there's a certain temperature, and if the universe were not expanding, you would have thermal equilibrium. So you can look at this process where you have neutrinos and antineutrinos, and then electrons and positrons can be absorbed and create neutrons and vice versa. And you got a thermal equilibrium prediction for the ratio of protons to neutrons. So the neutron is heavier, so it'll sort of go away. But then at a certain point, this will freeze out. So that means the expansion of the universe is preventing the number of neutrons to go down as fast as thermal physics. And that's also a probe of the expansion rate at that time. So if the universe were expanding faster, then you would get more neutrons that would be surviving. So this goes out of equilibrium. And then as we go to lower temperatures, the protons and the neutrons want to fuse to form deuterium, which is more tightly bound. So if this were the only reaction and there were a lot of time, we would have all deuterium, but then helium-4 is so much more stable. So you have to look at these reactions. And let me just point out a few features or bottlenecks to thermal equilibrium. So a neutron isn't charged, so apart from there not being enough time to have a direct collision, these can fuse to form tritium, but then when you have both nuclei charged, then there's a Coulomb barrier. And So you write codes with all the relevant cross sections and rate equations, and you get some predictions, which then can be compared to experiment. And this doesn't work perfectly. There's sort of a lithium problem, but you can fit the baryon to photon ratio. So if you have more than 2 elements here, then you have a prediction that can be tested. So this is a way of probing the earliest epoch directly, whether the nuclear physics that we measure today was can explain what happened in the first 3 minutes, and there's a lot of work to try to understand these different discrepancies. Okay, so let's go a little later to this sort of plasma physics epoch, so where the universe recombines and this proton alpha particle electron plasma turns into neutral helium and hydrogen. So these are the CMB photons. So this is much later. This is about 100,000 years after the Big Bang. If you put in the numbers in, the prediction of this theory is that you should have an almost perfect black body spectrum. And we can talk in later lectures about, well, that is not completely a firm prediction. There are tiny deviations that can be expected and teach you a lot. But this is a prediction to 1 part in 100,000 approximately. And this was a big challenge for people like Fred Hoyle, who wanted to maintain the steady state universe. So basically, the hot Big Bang theory says, well, the universe was in thermal equilibrium, and that's why you see this black body spectrum. So this is about when I was born a year earlier. This horn antenna at Bell Labs in the US, and basically Penzias and Wilson were doing radio astronomy half-time, and there was a lot of interest in communication. So they wanted to characterize the noise, so they made this steerable antenna. And we can talk a little more about the technology. And they discovered that you had this radiation that was very approximately black body, and that came from all different directions. And then it was pointed out by others, by Dickey, Roll, Peebles, and Wilkinson, that this would fit in with the hot Big Bang theory. But it took a number of years to really work out all of the predictions of that theory. So here is the, from the Kobe experiment, or the FIRAS far, this is a differential spectrometer, and the error bars on this spectrum are much smaller than the width of this line. So that's really a very important probe of the Big Bang theory, that there aren't large deviations from this black body spectrum. Okay, the same year in the same instrument, these are the maps of the cosmic microwave background. And this is at 53 gigahertz. And you see that if you just take a simple color scale, you see everything is at the same temperature. So that's sort of not very interesting. But if we subtract away the constant piece, then we see this dipole pattern. So this is hot, this is cold, and then you also see these are galactic coordinates. You see some little blemishes in our galaxy. So if we have a black body and then we're moving toward the black body, then looking straight ahead, you see blue and higher frequencies or a higher temperature, and the opposite behind your back. So this is the explanation of this dipole pattern, which had been seen before. And then they subtracted off the dipole pattern. And here you see these splotches and contamination around the galaxy. So we'll look at later experiments, and there will be higher resolution maps and attempts to very successful to subtract off the galaxy and just see this primordial part. But just to give you a preview, what the interpretation of this is that these are the initial perturbations, the irregularities of the universe when the universe was a thousandth of its present size. And by characterizing this and their statistical properties, we sort of see this initial surface. Now, it's not three-dimensional, it's sort of a two-dimensional shell that you're probing, but you have a certain amount of confidence that it's a fair sample of statistically of the three-dimensional distribution, because you see other evidence that we do not live in a special place. Okay, this is a more modern map. Let's see, going a little slower than I had anticipated. So I wanted to show you, so we say that the perturbations are small, so they're measured. If you take the temperature variation divided by the temperature, it's about 1 part in 10 to the minus 5. And this is here classical physics, and explains how an irregular universe can emerge from these very small initial conditions. So this is from Jeans in the beginning 20th century, I believe, and he sort of investigated. So this is the same, very much the same derivation as we would have for, sound waves, except we have gravity here, and like attracts like. And he showed, and you can do the if we had sound, we would get the second derivative of the density would be plus speed of sound squared. And then there would be a k, etc. But here you get this exponential growth and exponential expansion, and this time scale is about the same as the Hubble constant, which is not a coincidence. So basically, the conclusion of this analysis is that the slightest deviation from homogeneity is unstable. Now, of course, there's going to be gas physics. There's not just dark matter, but baryonic matter, and shocks are created and stuff like this. But this simple derivation without general relativity suffices to show that small initial conditions can lead to structure of, with density contrast. That's what this variable is, of order 1 at later times. So this is the theory, and we can do the same with general relativity, and we get the same conclusion. So here this is the expansion rate, and the expansion rate is related to the density, and then you can you get different scaling for the density. So if we just have ordinary matter, the particles have a certain mass, and this is just divided by the volume. Then with radiation, there's pressure, so you get a different exponent, and you can sort of work this out in a lot of different ways. A box with radiation, and you compress it adiabatically, and the wavelength is conserved, et cetera, et cetera. Okay. Well, I wanted to go to some more speculative physics, or now it's not considered so speculative, but what is the problem with this model? And it's basically, if we look at this metric, so ds squared is equal to 0 for light, then we can figure out how far light could have gone since the Big Bang. And we calculate this, and we get a sort of finite distance. And this is sort of a big problem for theory. So sorry for the French here. This is us here today, and time goes in the upward direction, and we can only show one of the spatial directions on this diagram. So here you have the Big Bang, and we'll...
Sorry, Martin.
Yes.
There is a question about your previous slide. It's about instability. Is this instability from homogeneity deviation is independent of the theory of gravity?
Well, yeah, that's a good question. I think to stop this instability, you would have to really alter gravity very substantially. And so I would say there being an instability is a rather robust prediction. But if you would have a different theory of gravity, let's see. So this is going back to this slide. So here we're just using Newtonian gravity. There's no GR or anything like this, anything fancy here. And we're assuming there are no non-gravitational forces. So on scales where, you know, for the dynamics of how galaxies interact with each other, if you believe normal gravity, this is rather conservative. There's also a lot of evidence for this being correct. And I mean, this is a bit of a digression, but it's an important point. So is there any other non-theoretical observational evidence for this picture? So here we have two modes. And if there weren't this gravitational instability, we might expect the velocities to be independent of the density. But it turns out that, you know, this growing mode, because it's exponentially decaying, is effectively not present if the perturbations started very early on. So that means that your density field predicts your velocity field, or if we can measure the peculiar velocities, that means the velocities that are not explained by this uniform Hubble flow. Then from the measured velocity field, we can reconstruct the density field and vice versa. And so the fact that you could do this reconstruction and they agree. So there are papers by Ecole and others, the potent reconstruction. They're
we seem to have lost Martin. Ilya, can you still hear Martin, or am I the only one who lost the connection?
No, I could also not hear Martin, and my internet was unstable. I was thinking that was my internet again. Okay.
No, I think it's Martin's internet, because I can see my router from here and it's still flashing, so it's still all right. Let's wait a second and see what happens.
Yeah, he's rejoining just now.
Okay, he's back. Welcome back. But you have to unmute yourself now, Martin.
Apologies.
No problem. That happened to the best of us.
Okay, can you see?
Yes, Martin, you're back in the system. Yeah, thank you.
Okay, so I would say to your question that because of these two fields, you know, the relation between the peculiar velocities and the density, that the gravitational instability picture has been verified observationally. Now, the ratio between those two, that's a more difficult question. So I hope that answers. That's an interesting digression. But I think it's also good to ask, you know, how could these things be different, you know, with that we should be exploring alternatives rather than just repeating the standard lore. Okay, so this is, if we go back to the horizon problem, okay, this is us today. This is the surface of less scattering. So this would be redshift 100. And then this would be the Big Bang. So we've sort of rescaled things. So light travels at 45 degrees and you know, there's quite a bit of distortion, but this shows the causal structure. So this is our backward light code. And the problem with the sort of standard cosmology, where you would just take this matter radiation equation of state and just extrapolate it backward and say, well, what else could it be? This predicts a sort of acausal universe. So if we have the CMB temperature on one side of the sky and then in the opposite direction agree within a part in 100,000, well, here there's no place where a light signal could have traveled to tell these two places to have the same temperature. So you could, of course, say, well, there was some higher being who just said that the universe put in these initial conditions and that's just the way it is. But you could be more ambitious and expect more than that. So that was the horizon problem, and Robert Dickey in the 1960s, when it was one of the people distressed this, that this is something that people should worry about. So the solution that came in the 1980s, I'm trying to think, we're close to the hour.
Yeah, Martin, if you find a natural point where to adjourn, I think that would be perfect, because I noticed that we already lost a few participants, and you know, in these times of COVID, maybe people have other commitments at 3. But I leave it to you. Yeah,
I would rather take some questions now, and we'll
perfect.
start next week with inflation, because it's an interesting subject that shouldn't be rushed.
That sounds like a good plan. And sorry, I don't want to steal Ilya's job.
Okay.
I don't see at the moment questions in the Q&A, but since we are not so many, I would also like to encourage the participants maybe to raise their hand, and we can quickly give them the right to speak. I'm sure we will have a few raised hands in a second.
Yeah, because we had a couple of questions
but
by the slides, yes, yeah, but I asked them, but maybe.
And I see that Yingshe is with us, and he usually has a question. So Yingshe, please raise your hand. Here we go. I knew that.
Okay, sorry. There is a question in the Q&A, and afterwards Inge can ask his question. And the question in Q&A is there concrete observational signature for inflation?
Maybe that is a question for next week.
maybe.
Yeah, I think that's a very interesting question without an easy answer, and also a question that the Nobel Committee might be debating. So I can come up with an argument, and I'll present it next week. But one side is that inflation just makes us feel good about things that people were assuming before inflation. So there's this Harrison-Saldovich people spectrum that people that fit the data rather well and has an extra scale symmetry. And inflation gives us satisfying explanation of how that might come about. And Gaussianity, people were analyzing how perturbations evolved using a Gaussian theory without any good reason, that inflation provides the ideology. And then there's also another side to it. So we'll talk about that next time in the pros and cons, because I think that frames inflation in a good way.
Thank you, Martin. And Yingxie joined us. Yingxie, if you have a question, or a comment, you're most than welcome to share it with us now.
Okay, thank you, Francesco. Yeah, just to check, can you hear me? Hello?
Yes, yes,
Am I
yes,
audible?
Yeah. Clearly, yeah.
Yes.
Okay, yes. Thanks, Martin, for this nice presentation. I wonder, so my question is really historical question. So you said by 1960s, Bob Dickey already realized that there is a problem of horizon. There's a kind of a horizon problem of the standard model of the cosmology. And so I wonder, did he just made this based on the isotropy of CMB that he saw, by this that Penzias-Wilson experiment and also the Princeton experiment, or by some other additional experiment that followed up in 1970s? So my question is basically about what made him to find this homogeneity problem of the standard CDM cosmology. Yeah.
Okay, I can tell you my guess at it. That this is sort of a history of science question. And Bob Dickey is a very interesting person because he has contributed a lot of things that are sort of highly theoretical and sort of almost engineering. So he really spans wide range of styles and skills in physics. This is in some lectures at the American Philosophical Society, and I think you will find it cited in that review article. I'm not sure. And it's something that doesn't seem to have gotten much attention at the time, and it's also sort of interesting talking about history. And for the Planck collaboration, we were faced with who really invented inflation. And, we could organize, this is a joke, a conference and have all the people come and fight it out among themselves. And so I think Alan Guth's paper, where he explains all of the problems and how inflation can solve them, even though his model didn't work. That was sort of really a break with the past. But I think that these were probably also problems that were talked a lot, but people didn't write as many papers as they do now. So if you can't solve it, you sort of shut up. Or that might have been the spirit of the time. But this would be a great subject for, a history of science investigation.
Thank you.
Oh, we have another with many.
Yes, I know Ilya wants to pick up on the 2 new questions in the Q&A.
Yes, there are a couple of new questions in the Q&A, and with many models and theories requiring a deep theoretical base and understanding of assumption, is there a place for a simplified or basic accepted physics equation in modeling of galaxies? Maybe go gather interest from younger or entry-level researchers.
Okay, this sort of modeling, like how to make galaxies and that kind of thing, it's not my specialty, but I can tell you what I understand about it and what's hard about the problem. So on the one hand, there you know, numerical problems, there are magnetic fields, shock waves, and fluid mechanics. It's supersonic fluid mechanics as well as gravity. So those are sort of well-defined problems. But then there's also, nobody really understands the physics on small scales. So stars create radiation and outflows and prevent other star formation. So, you know, there's a lot of sort of empirical modeling and subgrid physics. So that's an area where you write, well, good problems for young researchers. Well, they're good problems in the sense that they're difficult and they're things to do, whether one can solve them and make an impact. That's sometimes not so clear, but no guts, no glory. So I think that is something good to go into.
Thank you.
Okay, thank you. And another question is, you mentioned that some of high energy physics used to probe the Big Bang, and kind of that physics is not quite of equilibrium physics. During this time, was the universe ever at equilibrium?
Well, I don't know. I think that when people go back in time, you know, we tend to assume that the simplest story happens, and that's usually based on equilibrium physics. So jumping ahead, if we talk about inflation, the end of inflation is anything but equilibrium. So you have a huge amount of entropy production. If you have first order phase transitions, then you can also generate entropy. But we also have to think about, if we want to sort of look at things more observationally, and maybe I should explain this a little more in one of the next lectures. There's a lot that could happen that we will never see. But the basic picture is that, you know, unless you're rather far from equilibrium, that conserved quantum numbers sort of matter, and you know, then if you are at higher temperature, the baryon number, for example, and you know, maybe some things from dark matter that you can sort of describe a lot in terms of equilibrium physics. So I've evaded your question a little, I guess, because I don't really know how to answer it.
That's absolutely perfect, Martin. Thank you very much. And we have 3 more weeks to discuss it. Yeah. So, Martin, it seems we have no more urgent questions, and I'm sure our participants have a week now to think about it and come up maybe with further questions next week. So, Martin, thank you so much for being with us today, and thank you so much for an excellent lecture. And you saw that it raised a lot of interest and nice questions from the participants. Thank you also to Ilya and Yingche, who is still up there, and the panelists for being with us. And of course, thank you to all the other numerous participants that joined us this afternoon. So again, we will continue next Tuesday. And we will upload later today the video on YouTube. So if you know people that were interested but couldn't make it today, please invite them to watch it on YouTube, so that next week they can be back with us. So Martin, thank you very much. We wish you a good afternoon. Yeah, and we are really looking forward to see you again next week. Yeah. So thank you very much, Martin, and thank you, Ida, as well. Thank you. Thank you very much. All the best. Thank you. Bye. Thank you very much.